Hello there and welcome to another part on module 2. In this one we'll be covering the topic of instruction cycle. So we'll study what the instruction cycle is, and then we will see how the instruction cycle is used on the register reference, memory reference and input output instructions. We will also see a flowchart on how to determine which sort of instruction it is. And well, let's get started. As we know, a program is a sequence of instructions that are stored in a memory. Usually one program is executed by following a sequence of steps or passing through a cycle for each instruction. Thus, each instruction is subdivided into a sequence of subcycles or phases. So the instruction, it has phases or it has subcycles, which we'll be studying. The phases. The instruction cycle has four main phases. The first one is fetching an instruction from memory. So in order to execute any instruction, we first need to fetch it from the memory. And then the next step is to decode the instruction. This is the part where we understand what the opcode is, the address is, and the addressing mode. This is the part where we do that. Then at the third step, we read the effective address. That means the provided address in the instruction. We look for where the operand is stored. That is the effective address where the operand is stored. Okay, and this is found from the memory if the instruction has indirect address or whether it has direct address. On the basis of that, we can find the effective address. Finally, the fourth step in the instruction cycle is the execution of the instruction. This cycle repeats indefinitely, so you keep on going executing instruction after instruction until the halt instruction is encountered. This is the cycle. First we fetch the instruction, then we decode the instruction, we read the instruction, and then finally we execute the instruction and continue all over again. Initially, the program counter is loaded with the address of the first instruction. So the program counter gets the address of the first instruction, and the sequence counter is cleared to 0, providing a decoder time signal T0. So whenever sequence counter is set to 0, we get the time signal 0, and that marks the start of the cycle. After each clock pulse, the sequence counter is incremented so that we go on getting time signals from T0, we go to T1, T2 and so on. So this helps us in marking the phases of the instruction cycle. When we consider register reference instructions, as we had studied before, the register reference instructions are identified when these two conditions are fulfilled. I has to be 0 and D7 has to be 1. When these two instructions are identified, that is when the instruction cycle knows that it is a register reference instruction. Now D7 here over here represents to the decoder 7th output. If you remember, we studied about the decoder where it had 3 inputs of the opcode and it was giving us from 0 to 7 outputs for the 3-bit binary opcode. So D7 equals to 1 means that the opcode is 111, and if you remember the format of the register reference, it was 0111. So the opcode has to be 111 and the addressing mode is 0. Thus it is a register reference, and they are specified in between B0 to B11 of the instruction register. What this means is there are 12 different operations that can be performed, and this is the range of the operations. Execution of the instructions. The execution starts at time t3, and so whenever the signal is t3, that is when the execution of the program happens. The method of writing the register reference is denoted by R equals to D7 I dash, that means I is 0, and T3 where it is executed. BI equals to IRI, that means whatever instruction is being, the operation that is being carried out is stored at the instruction register position I, where I is from 0 to 11, that means 12 bits, and it determines the different types of operations. So at T0, the first step is that the instruction from the program counter is loaded into the AR. At T1, we read the address of the instruction from the memory and we store it into the instruction register. Along with that, the program counter is incremented so that it can point to the next instruction. At T2, We decode the instruction. The instruction is decoded from D0 to D7. We get the opcode, the IR from 12 to 14. This will be the opcode from the instruction register that is decoded. We also decode the 0 to 11 address and we store it to the address register. And then the ith bit, the I bit is also taken from the 15th bit of the instruction register. And this here is the decoding of the entire instruction. So the opcode, the address, and the addressing mode. This is done at T2. Here we have all the steps written in one place for the fetch and decode phase. So we have fetched in T0. We have also fetched over here. So after fetching it from the memory, we have placed it into the registers, and then finally at T2 we are decoding the instruction. We can use the basic computer instruction cycle to understand how the bus system works during these three steps. So we can give timing signals T1 and T0 as the loading for the AR and IR. We can use T1 to load IR and increment PC, and we can also use T1 to set the read memory operation. T0 on the other hand is used for loading AR, and T0 is also in the bus along with T1 for the select lines. Now at the first step T0, AR is loaded with PC, hence the selection line has to be 0 1 0, which is selecting PC to be transferred to the bus, and for that T0 has to be 1. When T0 is 1, so we get 0 1 0 and PC is transferred. With T0 1 we also see that it loads AR, hence the data from PC gets to the bus and it is then loaded into the AR. Then at T1, the timing signal 1, from memory AR we get it and we get the address and we store it into the instruction register. Here is the instruction register and we store it into the from the memory register. We put the instruction in the instruction register. We also increment the program counter. For this we have to copy memory to the bus, hence the selection lines become 1 1 1, giving us memory to the bus, and we also set T1 as 1. This way we are able to get 1 1 and 1 because we are having OR gates, and T1 is given to each of the OR gates, giving us the selection line of 1 1 1, which allows the memory unit to be copied onto the bus. We then also see that T1, since T1 is 1, it is turning on the load for increment for instruction register, and it also increments program counter. So it also refers to the read operation of the memory unit. Hence we are able to read from the memory, load it onto the bus and send it into the instruction register, as well as increment the program counter. This here is the flowchart for determining what type of instruction we have. The first step is the starting point where sequence counter has to be set to 0. Due to this we are able to get timing pulses T0, T1, T2 and so on. At T0 we copy from PC to AR. At T1 we increment the program counter, and from the memory we get the instruction and store it into the instruction register. At T2 clock pulse we decode the instruction. After decoding, now at this step we decide whether the instruction is memory reference, is it register reference or input output. So when D7, the bit D7 is 0, that means it will be memory reference register. This D7 proves that the opcode is not 111, it is anything but 111, hence it is memory reference. But if D7 is 1, it shows that the opcode is the combination 111, so it could either be register or input output. At the memory reference point we will now check for the I bit, that is the addressing mode. If the addressing mode is direct, that means 0, we will not be doing anything at T3 and we will directly execute the memory reference instruction at T4 and set the sequence counter to 0. The sequence counter is set to 0 so that we can repeat the cycle again and execute the next instruction. On the other hand, if the I bit, the addressing mode is 1, which means indirect. Then at T3 pulse, we are going to get the instruction from the indirect address, that point, and store it into the register, and then we are going to execute the memory reference instruction. Again, we're going to set sequence pointer to 0 to execute it again. Now looking for the input output as well as the register reference, the I bit in these two determines the difference between the two of them. So when I is 0, it is a register, and when it is 1, it is input output. Again at T3, in either case, depending on which case it is, we execute the input output instruction and set sequence counter to 0, and if it is a register case, we execute register reference and set sequence counter to 0. This way we are able to go all the way back again and execute the next instruction set. Just as we studied, this is the conditions for the register reference instruction. They are identified when D7 is 1 and I is 0. They are specified from B0 to B11 and execution at T3. Here are the register reference instructions from B0 to B11, and we can understand that each instruction has its own way of operating, and it has different micro operations that are executed. These are the memory reference instructions from D0 to D6. The effective address of the instructions is in AR and was placed there during T2. This happened, as we saw, when I was 0, or during T3 when I was 1. The memory cycle is assumed to be short enough to be computed in a CPU cycle, and execution starts at T4. As we saw, T3 was to determine whether it is direct or indirect. If it was indirect, we would copy it from the indirect address, so execution happens at T4. These are certain examples of how execution takes place. We can see that it's from D0 to D6. That is because D7 cannot be there. If it were D7, it would have been a register reference or an input reference, input output reference. Hence we have operations from D0 to D6. The function of memory reference register can be defined by register transfer notation. These instructions refer to memory address as an operand. The operand is always accumulator, and effective address of the instruction is in AR and was placed during T2 when I was 0 or T3 when I was 1. Memory cycle is assumed to be short enough, and the execution starts with T4. An example of execution is LDA, that is load to AC. Thus at D2, this function LDA happens at D2, execution is at T4. So we copy the address from the memory location into the data register, and then at T5 pulse, at the next clock cycle, we are able to send the data to the accumulator and set the sequence counter to 0. Another example is STA, that means store to the accumulator. So this is the D3 operation. Execution happens at T4, where the AC data is stored into the memory address. Sequence counter is set to 0 because we have completed the operation. BUN is branch unconditionally. This is D4 operation. It is again executed at T4. In this, the AR register is sent to PC and sequence counter is set to 0. BSA is another operation which is branch and save return address. This example is shown over here using the memory address, using the entire memory organization. So from the program counter, we store it into the memory address at the memory, and program counter is AR plus 1. As you can see, the program counter is stored into memory of AR, right? So program counter over here is 21. We see that this is before execution at T4, and then after execution this is the state. So program counter 21 is stored in memory address of AR. AR is 135. So at 135 the program counter is stored after execution, and then we also see that program counter is AR plus 1. We had AR as 135, so our program counter has been set to 136, which is AR plus 1, which is now pointing to the next instruction execution. These are the examples of memory reference execution, how the instructions are run. T4 is the execution time. If there are multiple steps that need to be performed, then multiple clock cycles and pulses are used as well. This is a flow diagram for different operations from D0 all the way to D6. Here D4, D5, D6, D0, D1, D2, D3, and these operations are performed in the following steps. Each block represents a clock cycle. So for AND we need 2 clock cycles. First memory is transferred to DR, and then we have ANDing in the accumulator through the accumulator logic, and then sequence counter set to 0. Thus at clock timing T5 we have completed the ANDing. At add we again transfer the address from memory to DR, and then we have the adding in the accumulator. We get the carry bit in E and sequence counter set to 0. Similarly, each of these operations are performed, and this is how the instructions are carried out step by step. You can go through them and try to understand the concept of how each and every instruction is executed. Input, output, and interrupt. Instructions and data stored in memory must come from some input device. The combination results must be transmitted to the user through output. So we need an input through some device, and the output is sent to the user through some other device. System for communication with an input device. Serial information is shifted into the input register. So for output, the output is stored in the output register, and for input it is sent to the input register. This is how the basic system looks like. We have a keyboard, which is an input device. It is connected to the transmitter interface, which transmits the data serially to the input register. We also have a printer, which is the output device, which is connected by the receiver interface, which is in place connected by the output register. So whenever we have an output, it is sent to the receiver, and that sends it to the printer. Same way, whenever we have an input, we send it to the transmitter, and it goes to the input register. We have the accumulator over here, and you may notice we have FGI and FGO. These are input flags and output flags. So FG is for flag and I is input, O for output. These are used for synchronizing the data transfer from the input to AC and from AC to output. They communicate with the AC serially and in parallel. They can communicate with AC in parallel, and they hold an 8-bit alphanumeric information. Input devices are usually slower, so we need to synchronize them. For this we use the FGI bit. It is a 1-bit flag, and it controls the operation. When FGI is set to 1, that means new information is available, and when it's 0, that means the computer has accepted the information from the input device. FGO on the other hand is the output bit flag. It is a 1-bit flag again. It's used to control the flip-flop and the output operations. FGO is set to 1. This means that the computer can send out information from AC, but if it is 0, that means the output device is already busy and the computer has to wait. The process of input information transfer is through these steps. Initially FGI is set to 0, and 8-bit code is shifted to the input register from the keyboard, and once it's shifted to the register, the FGI is set to 1. That means the computer is told that we have an input. As long as flag is set, the input cannot be changed, because we have to wait until the computer accepts the data. Once it checks the flag bit, if it is 1, the information is transferred parallelly to the AC, and FG is set to 0. Once the flag is cleared, then new information can be added into the input register. The process of outputting information follows these 3 steps. Initially FGO is set to 1, so the computer checks for the flag bit. If it's 1, then it is able to transfer the data to the output register parallelly, and once the data is transferred, the FGO is cleared and set to 0. The output accepts the coded information, and hence the printer is able to print the corresponding character. Once the operation is completed, the output device sets FGO back to 1. The computer does not load new data when FGO is 0, because this indicates that the device is busy. So whenever F flag is 0 in the output device, the computer waits for it to turn to 1, because 0 means that the device is busy. Input-output instructions are needed for multiple purposes, such as transferring information to and from AC, checking for flag bit, controlling the interrupt facility. The control unit recognizes it when D is 1 and I is 1. Since we studied, the input-output register input-output reference instruction is 1111, and the remaining specify the operation. The clock transition is associated with timings T3 as always. These are the following input-output instructions from B6 to B11. These are the instructions that can be carried out. To store the instructions and data in memory, input device is needed. The results must be visible to the user through output device, which causes the need of an output device. To communicate with the input device, the information is shifted into the input register, and for output it is used in the output register. This is the basic hierarchy. Thank you and see you in the next lecture.